Hello, in this session we will solve some of the numerical problems on the beams. In the last class we have derived the stiffness matrix for the beam element, that is 4 by 4 matrix EI by LE cube, and this matrix 4 by 4 size, where L is the length of the element, E is the Young's modulus, I is the moment of inertia, and in the matrix all the elements have the LE term, that is the length of the element. And in the beams problem we are deriving the nodal displacements. We know that the nodal displacements are vertical displacement and the slope v1 theta 1 v2 theta 2, and to find the nodal displacement again we are using the equilibrium equation. Kq is equal to F, where K is the stiffness matrix, this is the stiffness matrix for the beam element. If there are two or more elements, then we are using the global stiffness matrix. Then Q is the nodal displacement vector and F is the force vector. What is force vector? For one element, for this element, if the element is element which is loaded at the midpoint, then here considering these are the forces, this force and moment at node 1 and force at moment at the other end. Okay, similarly if the element where the load is UDL for the whole length, then at node 1 you are using the force P naught L by 2 and moment is P naught L square by 12. Similarly at the other end, force and moment are P naught L by 2 and minus P naught L square by 12. Okay, what are the force vector? It depends upon the what is the configuration of the element. If it is loaded at the midpoint, then you consider this equation. If it is loaded with UDL for the whole length, then you consider these are the forces and the moments. If it is UL, you consider these forces and moments. Similarly for UL of this type, you consider these are the forces and moments. Okay, if it is need to find the deflections, then use this equation to find the deflection. V is equal to H into Q, where H is the Hermite matrix and Q is the nodal displacement vector. Okay, H1, H2, H3, H4, it is derived in the previous video sessions. Okay, let us solve one problem on this. Okay, let us take this problem to solve the nodal displacement and to find the maximum deflections. It is a simply supported beam where one end it is fixed and the other end it is the roller support. Young's modulus is given and moment of inertia is given. Here Young's modulus value it is given, it is converted in kilonewton per meter square and forces are converted as kilonewtons. To avoid the bigger values, it is taken in this unit kilonewton meter square and forces are taken in kilonewtons. Now to find the nodal displacement, we need stiffness matrix nodal force vector. Let us find the stiffness matrix for the beam element. To find the stiffness matrix, what is required? LE and Young's modulus and moment of inertia. Young's modulus is given here 200 gigapascal, you convert it to kilonewton per meter square, and I is given, you convert it to meter raised to 4. So and the length of the element it is 1 meter. Okay, we have only one element here, so this is the stiffness matrix. K is equal to A by L cube, and substituting all the length of the element, we have this stiffness matrix. Now for this beam element, it is subjected to UDL. So what are the forces and moments at node 1? That is F1 and M1. Similarly F2, M2. It is given here in this table. When it is subjected to UDL, then at node 1, this is the force P naught L by 2, P naught L square by 12, where P naught is the what is the intensity of UDL loading and L is the length of the element. You find F1 and M1, and similarly F2 and M2. F2 and M2 are the force and moment at the node 2. These are the force vector. Now stiffness matrix of the element is determined. How you got EI by L? EI by L cube. E is the Young's modulus, I is the moment of inertia. It is in kilonewton per meter square, and I is meter raised to 4. So it is 400 kilonewton meter square. To avoid bigger values, it is taken in kilonewtons per meter square. Substituting all the length of the element, this is the stiffness matrix. Now we know that to solve into nodal displacement, KQ is equal to F, where K is the stiffness matrix. This is the stiffness matrix. Q is the nodal displacement. What are the nodal displacements for the element? For one element, there are 4 nodal displacements. For node 1, vertical displacement and slope. Similarly, vertical displacement and slope for the node 2. And force vector. In the force vector, force at node 1, moment at node 1. Similarly, force at node 2, moment at node 2. This is the force vector. It is for UDL, for the whole element. Okay, substituting P naught LE. What is P naught here? Okay, see here, P naught. This is the 12 kilonewton per meter, where this is the load of intensity, UDL intensity. This is P naught, 12 kilonewton per meter. I already told, when it is subjected to UDL for the whole element, then this is F1 and M1 at node 1 and F2 and M2 at node 2, force and moment at node 2. This is force vector. KQ is, you arrange in the KQ form, KQ, where K is the stiffness matrix and Q is the nodal displacement for the element 1, and F is the force vector. Substituting P naught LE values in all these terms, we have this vector. Okay, then by elimination approach method, in this problem node 1 is fixed. Node 1 is fixed means V1 and theta 1 are 0. So first row first column and second row second column, this first row first column, second row second column can be deleted. Similarly, node 2 has the roller support. Roller support means it can have only slope or rotation. There is no vertical displacement. So V2 is also 0. So third row third column can also be deleted. So what is left here? This 4 and theta. 400 into 4 theta, that is equal to 1. Okay, by this you will get a theta 2 value. So nodal displacements are 0, 0, 0, and by this theta 2 is equal to 6.25 into 10 raised to minus 4. And to find the deflections, usually when the loading is uniformly placed, the deflection it is at the midpoint. So V is equal to HQ. You substitute all the values here. H1 V1, LE by 2 H2 theta 1, S3 V2 and LE by S4 theta 2. As in our problem, Q1 V1 theta 1 V2 are 0. This term will be 0. This is 0. V2 is also 0. So this term is 0. Substituting theta 2 value and finding H4 and LE is 1 meters. Okay, the deflection is 7.815 into 10 raised to minus 5 meters. Okay, similarly we will solve some more problems in the next video session. Thank you.